We're going to have a look at one final example before we move into our last section from chapter 7. So we've got 10 individuals went on a low-fat diet for 12 weeks to lower their cholesterol. The data are recorded in the table below. We're going to use a significance level of alpha equals 0.05 to test the claim that their cholesterol levels were significantly lowered. You may assume that the necessary conditions are met. So the one big difference between this example and the one that we just looked at on the last page was that we're not given the summary statistics. We're going to have to go and find those values. So to start off, before we even get into that, let's start with our null hypothesis and our alternative hypothesis. So we have, let's see, starting cholesterol level, ending cholesterol level. Clearly, this is paired data. Anytime we've got before data and after data, that's usually a very big hint that we're going to be using paired data, which means that we're using the methods that we've talked about in this section 7.2. I wouldn't want to compare someone's starting cholesterol level with a different person's ending cholesterol level, right? Because there's a lot of different factors between their lifestyles. I'd probably want to just compare the one person's starting cholesterol level with their ending cholesterol level because their lifestyle is presumably going to be mostly the same between the beginning and the end, with the exception of this low-fat diet that they're on. So we need to start off with the null hypothesis and the alternative hypothesis, because that's our first step. So our null hypothesis, we've said that this is paired data. We sort of get the null hypothesis for free. So I'm going to take the average mean of the differences, and I'm going to go ahead and write it out because this time we are going to be doing a one-tail test. I'll explain why here. But I'm going to subtract. I'm going to take the average of the starting cholesterol levels minus the average of the ending cholesterol levels. And I know that because we're working with paired data, the null hypothesis says the difference of the means is equal to 0, right? So it's always equal to 0. We kind of get that one for free. So we've got that part, which means now we got to talk about our alternative hypothesis. So we're still talking about the mean of the differences. So that's equal to, let's see, mu sub starting minus mu sub ending. And so this time around, I am kind of making a specific claim that one of these is higher or lower. So we want to say that their cholesterol levels were significantly lowered. So significantly lowered. So if I subtract these two, if they were lowered, that means the ending value should be lower. So this value should be lower, which means my starting value would be higher. And I just want to think about this for a moment, because if I look at my null hypothesis, we said the null value was 0, which means we're still going to be using 0 here. So we really have three options. We could say less than, we could say greater than, we could say not equal to, right? Those are the three types of tests that we've been doing for hypothesis testing since way back in chapter 5. Now, in this case, if I take a higher number or a bigger number and I subtract a lower number, if I subtract those two, that tells me that I'm going to end up with a positive number, right? A big number minus a small number, I'm going to end up with a positive number, which means it's going to be greater than 0. If I had reversed them, if I had taken a smaller number minus a bigger number, in that case, I would say it's less than 0 because it would be a negative number. But that's not the case here. So when we have a bigger number minus a smaller number, higher minus lower, we are saying greater than 0 because the result should be positive. So we are doing, in this case, a right-tailed test. I do think that this is one of the trickier aspects of setting up your null and alternative hypotheses. Luckily, this is really the only step that we're going to have to deal with this, because at the end of this, when we go to find our p-value, we really only care that we're doing a one-tailed test here. But it does make a difference. It is something that we should be careful with. So we've got our null hypothesis. We've got our alternative hypothesis. The other thing that might not be a bad idea to go ahead and find here is to go and find that difference data, since that was not provided to us, which means we're going to have to take all of this data that was provided and punch it into our graphing calculator. So I've already done that here. Let me hop over. If you need to take a moment to enter that data in, remember you can press Stat and then choose number 1, Edit. I've already entered in the before data into L1 and the after data into L2. To find that difference data, remember, I'm going to scroll over to L3. I'm going to highlight L3, and then I want to take everything in L1 minus L2. So to do L1, I'm going to press second and then the number 1 minus second and then the number 2. And it should say L1 minus L2. We're going to go ahead and press enter, and there is our difference data right there. So that's wonderful. We've got that taken care of. And then the last thing I need to do is go find the difference data, which means I would like to know the mean of this data set, and I would like to know the standard deviation of this difference set. So the way that I'm going to do that, I'm going to press Stat. I'm going to arrow over once so that I'm under Calc, and I'm going to choose that very first option, 1 var stats. And if you have a newer calculator, you're going to see exactly what I have on my screen. It's going to ask for a list. Now, we do have to change our list here because our difference data set was in L3. So I'm going to press second and then the number 3 to change that list to L3. Now, if you have an older graphing calculator, you're probably not going to see this menu. It's just going to say 1 var stats, and it's going to be a blinking cursor after that. You need to tell the graphing calculator, hey, I want to look at L3. So you're going to press second and then the number 3, just like we did here. And then we're going to go down to calculate. If you have an older calculator, you should just be able to press enter, and you should end up with this same data set that we have right here. So if you have issues on that older calculator, go ahead and shoot me an email, and I can help walk you through that process. But my sample mean, my X bar is 9, and my sample standard deviation here is 24.244. So I've got these two numbers. X bar is 9, S is 24.244. So let's hop back at this point. We said X bar sub D, the mean of the differences is 9. S sub D, the standard deviation of the differences is 24.244. And the 3 decimal places is usually a good place to round to. The other thing we might want to pay attention to is our sample size n. We were told that we had 10 individuals, right? So our sample size is n equals 10. So that's pretty much everything that we've got in that first step. We've got our null and alternative hypothesis. We've also gathered up some information. Second step would be to go and check our conditions. However, our problem said you may assume that the necessary conditions are met. This is good because it might be a problem. Our sample size is relatively small with n is only equal to 10, which is not greater than or equal to 30, but this is not something I'm ever going to try and trick you on. It just says, hey, you can assume that the conditions are met, so we don't really have to do anything else. We can just say, okay, good, we're good to go there. Step 3, find the difference data set. And actually, I went a little bit out of order because we already did that. That was our step 3 right there. I usually like to gather that information in the first step of my problem, but doesn't really matter when we do it as long as we do it before we get to our calculation step. So we need to know our X bar sub D, our S sub D, and then our sample size n. So at this point, we've got everything that we need to go and do our calculations. Let's jump into that process. Step 4 right here. We want to find our standard error first of all. So our standard error, remember, is the sample standard deviation of the differences divided by square root of n. So in this case, 24.244 divided by the square root of 10. So let me go ahead and calculate that. Divided by radical 10, I ended up with 7.667 is our standard error. And then we should be able to go and find our test statistic. So our test statistic is a t-value. Remember, we're working with our t-distribution here. And we're going to take X bar sub D divided by our standard error. So our X bar sub D, we said that was 9 from way back up here, divided by our standard error, which we just found as 7.667. So we're going to go ahead and divide these two out. 9 divided by 7.667. And I ended up with 1.174, rounding to 3 decimal places here. So we've got that. Last thing that we'll need to find, the easiest of our calculations, we need to know our degrees of freedom, which is simply n minus 1. So that's 10 minus 1, or 9 right here. So we really need to know what is our degrees of freedom and what is our test statistic, along with the type of test we're doing. We said specifically we were doing a right-tailed test because we said greater than 0 in our alternative hypothesis, which means it's a one-tailed test. That's the row that I'm going to look at in order to estimate my p-value. So let me hop over to my t-table so that we can get our p-value. We said our degrees of freedom was 9, and our test statistic was t equals 1.174. So degrees of freedom as 9, we do have that row. We're looking at this row right here. That's what we're looking at. And then we said we were doing a one-tailed test because it's specifically a right-tailed test. So if I look at my test statistic, 1.174, it's going to be less than all of these values that we have in this row, which means that it lives somewhere over here. My p-value is going to live somewhere on that left-hand side. So if I look at the area in one tail, the p-value is going to live somewhere over there. And if I look at what happens as I move from the right side to the left side, I know it's a little confusing because we don't usually do that, but as I move from the right side to the left side, my p-value gets larger and larger every single time. It's getting bigger and bigger. So all I can say at the end of this is that it's going to be bigger than 0.1. So at the end of this, my estimation for my p-value, it is greater than 0.1. So hopping back to my problem here, based on our calculations, the p-value is greater than 0.1. So it's greater than 0.1. That's enough information for me to make my decision at the end of this problem. So we said our alpha that we were using was 0.05, the usual value. So the alpha is 0.05. So as always, we're going to ask, is the p-value less than alpha? In this case, because it's greater than 0.1, which is greater than 0.05, that means that no, it is not less than alpha. So that means because it is not less than alpha, we do not reject the null hypothesis H0, which means that there is not enough evidence to support the alternative hypothesis. So there is not enough evidence to support that. And I'm going to go back and look at the claim here so I can kind of mimic that language. It's tests the claim that their cholesterol levels were significantly lowered. So there's not evidence to support that. So there is not enough evidence to support that their cholesterol levels were significantly lowered. And there we go. That's the end of our problem. So hopefully we feel pretty comfortable with this process like we've seen before. You know, it's pretty similar to what we looked at in 9.1. In 7.1. In 7.3, our last section for Chapter 7, we'll look at how we deal with independent data and what makes that process different than the paired data process that we looked at in this section.